Bismillahirrahmanirrahim. Assalamualaikum. So let's proceed to next chapter, which is chapter 39, or according to our syllabus, this is chapter 11, Introduction to Quantum Physics. So if you see in this diagram, okay, we have a filament glowing. So the colors of the filament glowing here may vary according to the temperature of the filament. It starts with the red, orange, okay, and then finally the highest temperature, the color going to be white, right? Whatever we've learned before, considered as classical physics. Now onwards, we are going to take a look on the quantum physics, or also known as modern physics. Right? So why is it called as modern physics? There is a departure from the way classical physics treats a few experiments to the new method or approach in dealing with few findings. Okay, that is why we call it as quantum physics or modern physics. Alright, so the most important is about radiation produced by an element. Okay, so there is something that classical physics failed to explain. So let's explore. So in classical physics, thermal radiation originates from accelerated charged particles near the surface of an object. The way the radiation being produced is similar to the way of the EM wave produced by the antenna. There are few phenomena that fail to be explained fully by classical physics. Okay, some of the experiment is black body radiation, photoelectric effect, and hydrogen atom. So the way, the behavior, the output, the finding of this experiment or phenomenon are failed to be explained by classical physics in full. So physicists in that era figure out new method, we call it modern physics or quantum physics. But for our syllabus, we are going to solely focus on the photoelectric effect. This is the most important part, is Planck hypothesis. Okay, what's the difference between classical and Planck's hypothesis? Planck hypothesis says that the energy radiated by vibrating atoms only vibrated at specific energy. So these vibrating atoms, also known as resonator, okay, the one that going to resonate or vibrate. So the way it vibrate, okay, it must be at specific energy only. It's not like continuous. Specific energy. Okay, previously in classical physics, the physicists or scientists treat the EM wave produced by the radiating atoms in terms of continuous energy. So when it vibrates at specific energy, it means that it's not continuous. It means that it's in terms of packets of energy. Okay, the tiny packets known as quanta. Right, quanta also known as photon nowadays. Right, so if you can imagine, if this is a torchlight, okay, where the radiation is coming out from the torchlight, you can imagine that the radiation actually consists of tiny packets of energy radiated, okay, throughout surface or the area. Okay, it's not in classical physics we treat we treat it as continuous energy like this. Okay, it's not. Actually, it's packets. In terms of packets, tiny packets called as quanta, or also known as photon right now. So energy consists within a packet or quanta or photon is equivalent to HF in general. Okay, so why is it there is N here? The N here representing the level of the energy, the order. The N here known as well as quantum number. Okay, in general, energy consists within a quanta or photon is equivalent to HF, where the H is Planck constant. This is the Planck constant. You may check this from your constant in the calculator. And F is the frequency where the vibrating atoms or resonated vibrated at. And you also need to know conversion factor, because when we deal with the atomic level, the unit of joule is too big for it. So the common unit used is electron volt. 1 electron volt is equivalent to 1.6 times 10 to the power of negative 19 joules. The oscillator, the resonator just now, and the quantized energy. So if you can imagine the energy level within an atom or oscillator or resonator, okay, from 0, 1, 2, 3, and 4 until nth level, okay, for each of the energy going to be consist only HF, in the order of the HF. For the first level, let's say, is equivalent to HF. For the second level, it's twice HF. Okay, for the third level, it's 3 times of the HF. For the fourth level, it's 4 times of the HF. So this is the meaning of being quantized. The energy being quantized means that the energy is within a certain level, within a tiny or limited packets or amount. We also know the tiny packet as discrete amount. Double head arrow here indicates transition between adjacent state. It can move up or it can move down, right? So example 39.2, the quantized oscillator. A 2 kilogram block is attached to a massless spring that has a force constant of K equivalent to 25 Newton per meter. The spring is stretched 0.4 meter from its equilibrium position and released from rest. A. Find the total energy of the system and the frequency of oscillation according to the classical calculation. So what is classical calculation? Whatever we've learned before this, considered as classical oscillation or classical method or classical physics. So E equivalent to half Ka squared. Right? This is the amount of it. Right? And frequency is equivalent to omega over 2 pi. And what is our omega? Is equivalent to square root K over M. This is the original, if you still remember, right? And omega itself is square root K over M. Okay, so if our interest is to figure out the frequency, now substitute everything, you will get 0.563 Hz. B. Assuming the energy of the oscillator is quantized, find the quantum number N for the system oscillating with this amplitude. So as we know, N is the order or also known as quantum number. E for the n order or quantum number is equivalent to NHF. So you rearrange this equation, okay, use the energy calculated in part A, substitute with the over the Planck constant times with the frequency, you will get this amount of n order of number or quantum number. Lots of. That is why it seems like the energy is continuous, because the amount of the packet's energy is very large, huge amount. Right. Suppose the oscillator makes a transition from the n equivalent to this, the calculated one in part B just now, state to the state corresponding to the n equivalent to -1, means that the lower level, okay, the adjacent lower level. By how much does the energy of the oscillator change in this one quantum? So as we know, E equivalent to HF, and if we want to figure out En minus En minus 1 is equivalent to E level 1, isn't it? That is why we know it's equivalent to 1 times HF only. Your final answer is 3.73 times 10 to the power of negative 34 joules. Now let's proceed to photoelectric effect. Actually, the name of it itself explain about what it's all about. So in this experiment, electric is produced due to a photon, or simply also known as light or EM wave. In the beginning of the photoelectric effect experiments, okay, the Western scientists want to study about electric produced due to radiation of photon. So the basic setup like this initially placed within a dark area, right? So there is no electric current produced is observed. Whenever the setup is placed within area having lights, there is some current observed produced within this setup. Okay, so that is how the name of this experiment is photoelectric effect. Okay, so let's take a look on detail on how the mechanism of this photoelectric effect happen. Okay, in this figure, okay, it shows us evacuated glass, okay, or quartz tube contains a metallic plate E, okay, known as emitter, connected to the negative terminal, okay, of a battery, and another metallic plate C, known as collector, that is connected to the positive plate of a battery. So the voltmeter here plays a role to measure voltage difference between these two terminals of the battery, as well as the terminal between the collector and emitter. And emitter here plays a role to read the current flow due to the emission of the electron here. So the emitted electron here, known as photoelectrons. When the light strikes plate E, the emitter here, the electron going to be ejected from the plate, known as photoelectron. Then this moving electron going to collect by the C, the collector, okay, constitute producing a current flow within this circuit. Okay, by that means, okay, we're going to read current flow through the emitter within this circuit. All right. When this tube is kept in the dark, the emitter going to read 0 indicating that there is no current flow within the apparatus or circuit. The incident lights here, also known as photon. The ejected electron here, the moving electron here, also known as photoelectrons. Right? So the output of this experiment going to be observed like this. We will see that, initially, pattern of graph like this, right? Where we have here the current produced versus applied voltage here. From the battery, right? So what are we going to observe? Initially the response, when you increase the applied voltage, the current produced also going to be increased, and then it's going to reach one maximum level, or we call it I saturated current, and then not going to change anymore, a constant value. So whenever the voltage is equivalent to this point, the current produced is 0. So the delta V whenever current is 0 is negative delta Vs. We call it as stopping potential. So this is the output of the experiment when we are using one light or photon within certain amount of wavelength. Right. If we repeat the experiment with another type of lights, we are going to observe another response in similar pattern. But then the amount of the current produced will be bigger because of the high intensity of the lights, second light or wavelength being used. However, the pattern is still the same, and the value is still the same for negative delta Vs. How to do the negative delta Vs? We are going to change this. If you see the arrow here, it means that it's variable. You can change it. You can reverse the polarity as well, instead of change the value of the voltage. Right. So whenever you change this one, the applied voltage is same, and then the current, the current will be varied accordingly initially until it reach one maximum level and no more change. We call it saturation current. Whenever current is equivalent to 0, that delta V is equivalent to negative delta Vs. This is known as stopping potential. On classical physics, the photoelectric effect is dealt or treated within the concept of energy conservation. So it says that sum of the change in the kinetic energy plus change in potential energy in terms of electric must equivalent to 0. Right? Because no energy should be created or destroyed based on conservation of energy. Right? So from here, change in kinetic energy, it means that kinetic energy final minus kinetic energy initial. And the kinetic energy final is equivalent to 0 because finally the photoelectron going to be stopped. There is no movement. Initially it's moving from the emitter to the collector. Right? Finally it is collected by the C and being stopped. That is why we call this variable known as stopping potential. Then, the change in potential energy in terms of electric, okay, we know that potential energy in terms of electric for a moving charge is equivalent to QV. Okay, so for this case, Q delta V. For this case, our Q is the electron, negative E. Alright, times the voltage applied is negative delta V S. Okay, this is the final. Okay, minus the initial is 0 because whenever there is no applied voltage, the photoelectron is not being ejected yet. Okay, there is no potential. Okay, no potential, no ejection of the photoelectron. So finally, after you applied the voltage, then you are going to see or you're going to observe the photoelectron going to be collected, okay, by the collector and causing the current flow within the circuit. That is why for UE final is equivalent to negative E times negative delta Vs. So from here, okay, we can simplify the equation into negative K initial. Supposedly, this one is positive. We substitute the delta V with negative of delta Vs. It means that, okay, the electron that stops immediately before reaching plate C has a maximum possible kinetic energy upon leaving the metal surface. The previous equation, okay, can be rewritten as Ke maximum, kinetic energy maximum, is equivalent to E delta Vs from here. Okay, and our K initial here is K max. The photoelectric effect and the particle theory of lights. Okay, why is it the title of it saying about particle theory of lights? Actually, in classical physics, the light treated as wave. There is no idea at all that the light can become or behave as particle. So let's take a look. The wave theory predictions. Okay, photoelectric effect should occur at any frequency, right? But from the observation being done, no electron emitted for frequency below cut-off frequency, or we also call it critical frequency, right? Light intensity increases, okay, where K of the photoelectron also going to be increased. This is the prediction of the wave theory, or also known as classical physics. However, within the observation of the experiment, it is figured out that kinetic energy maximum independent of the light intensity. So it's not depending on the light intensity or incident light intensity. Then, third one, no relationship between photoelectron energy and light frequency because it's considered as a wave. But the real observation is light frequency increases, kinetic energy maximum of the photoelectron also increases. The fourth prediction by the classical physics, photoelectrons need time to absorb incident radiation before escaping from the metal. So means that if the light intensity, the low light intensity being used, if we give time for it, let's say 1 hour, 2 hours, okay, then the energy being absorbed by the electron going to be enough then the electron going to be ejected or escape from the atom or the emitter plate. However, that is not happening. So what is happening actually? Electrons are emitted from the surface almost instantaneously, even at low light intensity. It does not need long duration to collect the energy then being ejected to the out of the metal. So now, Einstein's model for the photoelectric effect. Right. So based on Einstein model, okay, it's not only using classical conservation of energy. Now it's involved the transfer of electromagnetic radiation, where change in kinetic energy plus change in electric potential energy must equivalent to the transfer of energy in terms of electromagnetic radiation. As we know, K final is K max minus K initial is 0, it's not moving yet. And electric potential energy final is equivalent to 0. And electric potential energy initial is equivalent to negative of work function. So some new things introduced here where it is equivalent to work function. So what is work function? Work function is actually minimum required energy to eject an electron from a metal surface. So this minimum required energy is used up to break the bond between the electron to the atom within the emitter, right? And this work function is different from one metal to another type of metal, right? Is equivalent to the transfer of electromagnetic radiation is actually the energy consists within a photon, which is our incident lights within the experiment of the photoelectric effect. From here, kinetic energy maximum plus work function is equivalent to HF. This is actually also referred to conservation of energy, but in bigger picture where we consider the transfer of energy in terms of electromagnetic radiation or energy within our incident photon or incident light. So from here, if we would like to have kinetic energy maximum for our photoelectron, the ejected or emitted electron is equivalent to the energy within the incident photon or light minus the work function of the metal. Remember, work function is minimum required energy to eject electron from a certain metal. If you see table 39.1 here, listed here work function for selected metal. So if you see here, natrium 2.45, 2.46 EV, aluminium 4.08 EV. Still remember what is EV? Electron volt. We are using electron volt unit because the joules unit is too big, way too big for movement of electron, right? And so on. Okay. Note here, values are typical for metal listed. Actual values may vary depending on weather because temperature play the roles for the vibration of atom. Okay. The matter is a single crystal or polycrystalline. Values may also depend on the phase from which electrons are ejected from crystalline metals. Furthermore, different experimental procedures may produce different values. But for your level, we consider this as a constant value. So, based on the Einstein prediction or concept, we can plot that kinetic energy maximum versus a frequency, producing a linear graph like this. And when we have kinetic energy maximum equivalent to 0, the frequency is known as cutoff frequency. And if you extrapolate the data, you will figure out that negative of kinetic energy maximum is actually the work function for that metal. Right. So in terms of conservation of energy made up by the Einstein, okay, it is known here delta K plus delta U in terms of electric mass equivalent to transfer of electromagnetic radiation. So what is the delta K? Delta K happen here. Okay, here is K initial, here is K final. And the delta U happen here as well. The delta U initial is here, U final is here in terms of electric. For the photon, the incident lights, okay, that causing the ejection of the photoelectron, the energy is equivalent to HF, right? And the energy, minimum required energy to eject an electron for particular this metal is equivalent to work function, which is equivalent to HFC. So now if we substitute all this, okay, K final minus K initial plus U electric final minus U electric initial equivalent to HF. That is the energy being transferred by the photon, right? So kinetic energy final is equivalent to K max initial 0 plus UE final is 0 minus negative of work function. Then you will have K max plus work function is equivalent to HF. Explanation of observation in the correct way or in modern physics, or we also call it in quantum physics, okay. So the observation, okay, kinetic energy maximum for the photoelectron independent of light intensity. Why is it so? Because the kinetic energy maximum is equivalent to HF, Planck constant, times with the frequency. This is the energy from our photon or incident lights minus the work function of the metal used as the emitter. No dependence on intensity. Within this formula, there is no intensity. That is why this happened. Alright. Electrons are emitted from the surface almost instantaneously, even at low light intensity. Okay, why is this happening? Because the light energy is in packets. Still remember the Planck's hypothesis? Okay, the amount of the energy is in discrete amount or tiny packet. We call it quanta. Right, no time needed for electron to acquire energy to escape metal. Okay, if it is enough, it is correct wavelength, it is correct frequency, then it's going to be ejected immediately. No electron emitted for frequency below than critical frequency or cut-off frequency FC. Okay, why is it so? Because the photoelectron created by absorbing single photon. Okay, remember in classical physics, okay, the radiation by the atoms is considered as continuous energy. Okay, by modern or quantum physics, okay, the radiation by an atom considered as a single resonator or vibrator, coming from single resonator or vibrator. That is why we call it single photon. Okay. So whenever the photon energy, which is the incident light's energy, is bigger than or equals to work function, the minimum required energy by the metal to eject an electron, then you're going to observe photoelectron ejected or created and absorbed by the collector, where it produces current flow within our experimental setup. Last one. Light frequency increases where kinetic energy maximum of photoelectron increases. So why is this happening? Because the kinetic energy maximum of the photoelectron is linear in F. Based on what? This equation as well. Okay? And for work function, we also can use HFC. Right? So means that kinetic energy maximum is directly proportional to the F. That is why, okay, kinetic energy maximum of photoelectron, okay, directly proportional to the frequency. Whenever frequency increase, the kinetic energy maximum also going to be increased. Okay, so now let's take a look on detail on the work function and cut-off frequency. So as we know, kinetic energy maximum is equivalent to HF minus work function. And work function itself is actually HFC. So from here, FC is equivalent to work function over H. H is Planck constant. Alright, so lambda C is equivalent to C over FC. So C is the speed of light within vacuum or air, which is 3 times 10 to the power of 8 meter per second. And we know that cut-off frequency just now is equivalent to work function over Planck constant, where from here we can have HC over work function is equivalent to lambda C. Right. So if you substitute everything here in SI unit, you will get in terms of meter for lambda C. Right. However, you have another option. If let's say your work function is in EV, right? HC here, you can use this value in terms of EV dot nanometer. Okay, then you don't have to convert this one. This one is converted to you directly. Okay. So we have a graph here of kinetic energy maximum versus frequency. Okay, from this graph, okay, when you do the extrapolation, you will figure out negative amount of kinetic energy is actually work function for this metal. Right? Again, when you repeat the experiment with another type of metal, you are going to observe some data and plot it. And whenever you extrapolate and figure out the amount of the kinetic energy for minimum value of it, you will figure out this is work function for metal 2 and so on. Okay, the data show a linear relationship between kinetic energy maximum and F with the slope the same for all metals. Okay, so this is as predicted by the Einstein model. Photons with frequency less than cut-off frequency for a given metal do not have sufficient energy to eject an electron from the metal, right? So application of the photoelectric effect is One of it is the photomultiplier tube. Okay, an incoming particle enters the scintillation crystal where the collision results in a photon. The photon strikes the photocathode, which emits an electron by the photoelectric effect. This is the main concept used. The light collected by a telescope from a single star is allowed to fall on a photomultiplier tube for a time interval. The tube measures the total energy transferred by the light during the time interval, which can then be converted to a luminosity of the star. That is how we observe and we figure out this is what star and which star. Example 39.3, the photoelectric effect for sodium. A sodium surface is illuminated with light having a wavelength of 300 nanometers. The work function for sodium metal is 2.46 eV electron volt. Find the maximum kinetic energy of the ejected photoelectron. E is equivalent to HF and F is equivalent to C over lambda. So based on the formula for kinetic energy maximum is equivalent to HF minus work function. Okay, you may substitute HF with this, HC over lambda, and use the conversion factor of HC, right, minus the work function given here. You will get 1.67 electron volt. So this is the kinetic energy maximum that the photoelectron can have. Find the cut-off wavelength lambda C for sodium. Work function is equivalent to HFC and H times with the C over lambda C, right? So from here we can rewrite this. Lambda C is equivalent to HC over work function. Okay, then substitute the value. You will get the lambda is equivalent to 504 nanometer.